So welcome to today's mini lecture. So this mini lecture is supposed to be used as a supplementary material to the lecture by Professor Ankur Moitra that I shared on the Teams portal. So this is not supposed to be used as a standalone lecture. So this is a supplementary lecture so that you to help you grasp some of the concepts more effectively. So in that lecture, what we are talking about is tensor decomposition. So we saw the problems that we have in matrix decomposition. That the matrix decompositions, even singular value decompositions, they are invariant to unitary rotations and stuff like that. That is why we go to tensor decompositions, and then the lecture discussed some initial thoughts on tensors and all those things. So we will discuss three main points in this lecture. The first point will be to reinforce what tensor is and what tensor decomposition is. In the second point, we will, and in the second and third points, we will discuss some subtleties of the generic algorithm. Not exactly subtleties, but some details of the generic algorithm by using an example so that it helps you understand what is going on. Okay, so first we move on to the tensor decomposition using an example. Suppose we have a tensor of this form 0, -1, 1 and 0. Okay, so let's say this is the tensor that we have. So tensor is basically stacked matrices. So this is a matrix and this is a matrix. So we say that these two matrices are stacked on one behind the other or whatever. So that is basically a tensor, an array of matrices. So one of the ways of decomposing this tensor is the following. Okay, so this is what he calls in his lecture that this will be A1, this will be B1, A1, B1, C1, this is A2, B2, and this term is C2. Okay, so next we will just quickly do some elementary calculations to give you an idea of how the original tensor is reconstructed by this decomposition. Okay, so the first part will be just to take the standard product of these A1 B1 transpose. What we'll be doing is just A1 B1 transpose, and when we do that operation, we will basically get 1 I minus I and minus I square. So I here is the complex number that we have. Minus I square will be plus 1. This is what we will have, and we will just write 1 and minus I as it is. Okay, because we just know that it is here, or maybe we'll just put a tensor product, and on this side we will have 1 minus I and minus I square. So minus I square will just again be 1, and we will keep the tensor as it is. Okay, so what we mean to say here is that, so when we multiply this matrix A1 B1 transpose by 1, and when we multiply this matrix A2 B2 transpose by 1, and when we add, we will get the first matrix of the tensor. Okay, so that is what we will see here, 1 I minus I 1. So this is the matrix that we obtain when we multiply A1 B1 transpose by 1. Similarly, when we multiply it by minus I, so we will have minus I square will be 1, and we will have again minus I square here, so we will have plus 1, and here we will have minus I. Okay, so this is what we will have, and on this side we will have 1 minus I 1, and when we multiply by I we will have I 1 and this will be, just a second, I think I made some mistake. uh, okay, this will be I1 and this will be I square. It will be minus 1 and we will have I again. I think I made some mistake because plus I square. So then this will be minus 1. Okay, so here I made the mistake here. So this will be actually minus 1. I do not know why the eraser is not working. Okay, because here we'll have plus I square, and plus I square is minus 1. So when we add these components, okay, so what we get is 2, 0, 0, 2, and when we add this and this component, then we get 0, 2, minus 2, 0. Okay, so actually our decomposition had 1 by 2 also. So if we divide by 1 by 2, we will get the original tensor. Okay, so what we are discussing in that lecture is that we have a tensor and we want to decompose it into tensors of this form. So these are like low rank tensor or whatever. Okay, so this is what, so this exactly does not fit into the algorithm because there are some subtleties with rank, but we will not discuss those things here. Okay, so this finishes the first part of what we want to discuss in this mini lecture. And then the second part is the generic algorithm. The second part is generics algorithm itself. Okay, so what generics algorithm is saying is that if we have a tensor, we will again consider the same tensor 1 0 0 1 0 1 minus 1 0. So we have 1 0 0 1 and we have minus 1 0. Sorry, z. We have 0 minus 1 1 0. Okay, so was that right? 0 minus 1 1 0. Okay, so what generics algorithm is saying that we will generate a two-dimensional at random. Okay, so at random, and then we will add. So if we have a tensor which looks something like this, then we will generate a random vector x and we will weigh each of these slices. These are all matrices. Each of these slices by the component of x and add them together to form a matrix. So we are sort of compressing this cuboid, or we are compressing this cube to a square. So by using a random vector from the sphere. Okay. So here let us assume that the vector that we have is x1 and x2. So when we scale these matrices and add, then what we will obtain is x1 0 0 x1 plus 0 x2 minus x2 0, and the resulting our compressed matrix will be x1 x2 minus x2 x1. Okay, so this is the idea that from a tensor we will create a matrix and using randomization and something. So in the lecture what he is telling is that we can also look at, we can also perform this operation in the decomposition. Okay, so our objective is that we want to decompose the tensor as into three, into a tensor product of three vectors, where when we do the decomposition, let's say we need something like this over all I, and the rules that he has talked about is that AIs, BIs and CIs are independent to each other. And the idea is that we want to scale the tensor. If we had the tensor, then the scaling will look something like this. But suppose if we have the decomposition given to us, we will reverse engineer it. Then the decomposition looks something like we have a dot product of Ci and X, and we create a diagonal matrix. So what we have is A dx into B transpose. So the tensor can be written like this. So this is what he has claimed, where AIs are the columns of A, B transpose we already know, and dx is the inner product of Ci and X. Okay? The inner product, or the di is the diagonal matrix in which the entries are the inner product of Ci and X. Okay, so we will just look at what this means in the for the example that we have. So our A matrix will be 1 minus I 1 I. So we had 1 minus I 1 I. B matrix will be 1 I and 1 minus I transpose. So our B matrix will be 1 I 1 minus I transpose. So when we take transpose, we will have 1 here and I here. Okay, so this is what we will get, 1 here, I here. And our diagonal matrix is just Ci times X. Okay, so our first Ci was 1 minus I. So we will have x1 minus I x2. And our second was 1 comma I. So we will have x1 plus I x2. So we will have x1 minus I x2, 0, 0, and x1 plus I x2. Okay. Now, you can verify at home that when you multiply these three matrices, eventually what you will get, you also have to do that 1 by 2. Okay, so just keeping those factors in mind, what we will 1 by 2 or whatever, what we will obtain is the left hand side will be x1 x2 minus x2 x1. Okay, so just be careful with all the 1 by 2's that we will have here. Okay, so this is what we expect to obtain. Okay, so this was the second point of how we are representing this tensor decomposition in terms of a generic algorithm in terms of decomposition. And then the third important part was that the matrix that we obtain. So we had something like what we had two matrices, and we took the inverse of the second. So we generated two random vectors. We scaled the decompositions by that, and then we did something like this: t of x and t of y inverse. And then the main claim was that the eigen, I mean the diagonal matrices which we will obtain will basically be, so we will have let's say dx dy inverse. Okay, so this will be the diagonal entry when we multiply these two matrices. So that will be ci x divided by ci y. Okay, so now ci's are independent of each other. So there is no chance that the diagonal entry will be 0, because I cannot sum all the CIs together so that they sum to 0. Okay, so you get the idea. And then the second is that then the second claim is that all the entries are distinct. Okay, so all the entries are distinct. That happens because there is very less chance that we will pick x and y to be same over two iterations, because we are picking randomly and that is a zero probability event and something so that is why we have the almost surely guarantee. So these are the three things that I just wanted to gloss over as a supplementary material to the lecture that I have posted. This is not meant to be a standalone lecture. Thank you.